Today's talk is Physics for Engineers, Units of Measure Challenges Teaching Torque and Angular Momentum. It's taught today, physics is taught with two separate concepts. There's linear force, momentum, and things like that, which is taught as, say, kilograms times meters per second squared, or kilograms times meters per second, or momentum. Similarly, angular momentum or rotational acceleration is taught as meters times kilograms times meters per second. So there's this extra meters time. However, equations are very difficult. How does an engineer then do a transfer between the two systems? And the way we're teaching it today makes that a challenge. Today I'm going to show you a change, and I believe it's a change to the existing textbook, because I teach this as a dimensionless scaling. So whenever you hear the word dimensionless, understand that for physics, you're trying to usually do some sort of a comparison, something inside, say, an exponent, or something that's a scaling. And here, instead of doing meters, we're going to do distance of the arm versus the distance of the center of mass of that half. And then you have to do both halves. So you've got to think about it like this. If you've got two of them, you split into doing this half, and you split into doing this half. And then you have a calculation of the whole, but now you have an arm for your rotation. You have the arm so that as this rotates, you can calculate that, but it's the same units of measure. So for reference, I'm going to show you this as force is usually called mass times acceleration, and that torque, this tau function, is this extra r, the length of the arm, times that force. And so it's using a different units of measure. So we're getting meters times meters per second squared, which is acceleration, times the kilograms. And so you end up with something that looks like meters squared times meters second squared over kilograms. Okay, and at the right, you can see that really this is the arm, and then you have this one force. Okay, but it's missing the scaling that I'm talking about. Now, the same thing applies with energy. Okay, so you're trying to get the momentum of something, and that's mass times the velocity. Similarly, you can do this for a rotational using the function L, and again, you just add that extra r. And similarly, we go through this work function, okay, which is very similar. Again, you get this meters times meters per second squared times kilograms as the units of measure. So what is this configuration? So instead of the angular momentum function, which gets applied as a function, you have to think about this as a time frame, because at that time there is a force inward and a force outward, and we get this thing with the radius and the speed thereby becoming this, but that only applies in perfect orbits, like Bohr, except that isn't the physics half the time. And so this is going to be applied for those times that are not a gravitational orbit. Similarly, this is what happens for momentum on the rotational basis. So this is a false equivalence. Torque is really a force, but it has a different units of measure. Work and energy is applied has this units of measure, a kilogram meter squared, which is a momentum concept because it's doing the square of the meters and the seconds, this squaring process. Students get confused between a force and a momentum. But when you apply, and when we fix the textbooks to do this better scaling, net-dimensionless scaling, it will work better and cleanly. So let's define the terms. So if we have an object, you take the object, and somewhere here in the center, we have a center of mass, okay? And all the linear things can be applied. We're sort of doing a nice guess that all the objects go to this point equation there, and your linear terms will work fairly well, although there's some adjustments if you're close, but if you're at any distance away, then the point equation method works great, okay? Once you get close, it has some challenges, okay? But here, now you have a left half and a right half, and you can calculate the center of that, and you have an arm. So now you have that extra r, okay? But now, where is the center of mass of this? Where's the center of mass of this? Now, these are spheres, so we know that the left position is at, um, for a sphere, is 3/8 times of the whole radius is the center of it. So it's not halfway out, it's only 3/8 because there's more mass here. Now, each object you would have to do. That's why I'm using the word half. But a hemisphere is a nice, good thing that you can understand as the first simple example. Now, we have to then define where those forces are relative to those three positions. So as the object comes in, you get a object, okay? And there's a center of mass, but then there's a center of the half. Now these are cylinders, so this one is easy. It's halfway out, and this one has halfway out. So you have the object, then you have the center of mass of the left, and you have the center of mass of the right. Okay, so these are the three positions. Now you determine where the force is. Is the force here? Is the force here? Is the force here? And you can do a formula of compute this half, sum them, compare. That tells you how much goes to rotational, and then whatever's left over goes to the center and becomes the linear based upon a point equation. Okay, as the best example or fairly good example. Okay, so what happens if we send this, okay, with right here at the center of mass? Well, at that point, we've got the transfer of this one, okay, and that's at -1, okay, and you've got this one, which is a +1, but remember, you're doing the two halves and you reverse them, so that's becomes a -1, so that's a plus. And so the formula here is that the amount that this is getting, when you push here, this one is getting pushed to leave, and this one's getting pushed to leave, but effectively those two balance. So that when you do this, and you hit right here, it goes exactly straight. And if you're lucky, and in class I give an example on a table, and it shows that if I can do it really well, I can move this without the sides doing thing. And so this is the simplest example. Now, another example is where I go inside of that. So now the question here is that position is negative for one, but positive for the other, okay? So it will get some rotation because the distance to the opposite half is larger, and the scaling is distance to the center of mass, and this has to have the full distance to the center of mass of the other half. So now you get the other half getting the greater torque. Okay, so as you hit here, this one has a small torque going this way. This one has a large torque going this way, and this side wins. And so the net transfer is that this will spin that way. So now, how do I get this to transfer entirely to rotational? Well, I've got to get this half and the other half. Remember, you have to get both masses going in the same direction. But if I move out, I don't have to move 2. If you look at this spacing, if I move out 1.5, I'm going to be 1/2 the red away from the current one, and I'm going to be 3/2 away from the far one. And so the 1/2 minus the 3/2 is 2, okay? And that means that I have enough mass applied to this one item that it's going to make 100% transfer to the object. So today is, in conclusion, teachings using a one-side variable, okay, not scaled, fails as teaching, okay? This is one of the problems. We need to get torque units of measure correctly. And now when I do this, the units of measure of angular is still kilograms times meters per second squared, newtons, okay? And for linear, it is the same. So the transfer works, and you can engineer this precisely. But you have to do that second extra step. So we have great challenges in teaching, and part of it goes from how we teach these basic concepts, like A equals F over M for Newton's things. So my questions have been to colleagues, how do we change the thinking in the textbook wording for torque? How do we get this so that a force is a force? All right. And your questions from the audience included, does this have other applications? And the answer is yes. When we get to quantum mechanics, we constantly use this angular momentum and the Bohr model. But if you think of particles and you think of figuring out the arm, now we have a method to make the units of measure not meters squared over seconds squared, which is then the square in the Born rule, but a method to do this. This has great implications, but I don't have the time for that in today's presentation. Thank you.